Good morning. I'm going to make the presentation on energy storage, so there will no any chemical reaction or atoms. So I try to just make at very high level my presentation. So you can see that the sources of energy is divided on 5. You have solar, hydroelectric. You have nuclear like fission and fusion. You have geoenergy and wind energy. However, for energy storage methods, we divide into 3 methods: is carbon storage, electrochemical storage like lithium, hydrogen, and redox flow, and physical storage. We have kinetics energy, potential energy, and also compressed air. You're going to see presentation compressed air today. So, advantage of carbon storage. Carbon storage has very high energy density, around 11,000 watt-hour by kilograms. But however, the charge is very long. We need years and years. So when you go to biomass, so we have between 3 years to 25 years. However, when we use petroleum or gases, you can see that the energy yield is around 30%, and we have a problem of pollution and green gas emissions. So because of wind and solar, which is intermittent energy, we need energy storage. And then energy storage, you can really get different type of energy storage, especially I am focused more on the battery, what we are doing here. So you see there are many types of the batteries. Maybe you can know the lead acid battery that we have in our cars. Nickel cadmium, this is what is in our toys. And nickel metal hydride was the first technology that Toyota introduced on HEV and lithium ion. Why lithium ion? Because energy density watt-hour by kilograms is very high, and watt-hours by liter by volume is very high. And you can see lithium ion, since Sony was introduced the technology in 1991, this technology was changed our life. You can see any iPad, iPhone, or what you can see, and also electric vehicles, storage, space, medical are using lithium-ion batteries. Kilowatt hours and megawatt hours. And you can see, let's see what you see on watt hours. This is laptops, iPad, and so on. The market is around 10 billion in 2017. Unfortunately, this will be stable, will be decreasing because energy density of the battery will be increased and become thinner. So we can see this market will be stable for next years. However, for electric vehicles, the market will be huge. So between 160 billions to 200 billions in 2030. And the energy density, what you call it, megawatt hours, this is energy storage. I believe the market will be reached 7 billions very quickly between 2025 and 2030. So there are many applications also when you go to energy storage, because when electric vehicle will be increasing, so become like, let's see, if we have 1 million of electric vehicles and they need 100 kilowatt hours, so we need 100 terawatt hours in order to charge these cars. So we need to have smart grid, and we need to have vehicle to grid or vehicle to edge. So vehicle to grid, there are two-way energy flow. So I believe this one, now we can see like Mitsubishi and Nissan Leaf are introducing vehicle to grid to the market. Hydro-Québec has developing electric motors and also the technology of vehicle to grid. So other thing also, when I come to the market, because I believe there are many economics here, you can see that acceleration of energy storage, especially in electric vehicles, because electric vehicle also you can use them vehicle to home, in your home when you have like blackout. And you can see this is explain the market that all the company, automotive company like Volvo, Toyota, Mercedes-Benz, GM, BMW, and others, at least by 2025, that 25% of their car become electric, and they want to introduce minimum 25 models. And this is showing also that the market here, you can see, is between 160 to 200 billions. This is only batteries. It's not including cars, not including, so you can see it's a huge, this is mainly on energy storage. The battery technology, I'm not going in details. Right now, what you call it lithium ion, because on the battery you have anode, cathode, and the electrolyte. And then mainly you can see iron phosphate, or you can see cobalt. And we are working on green and circular economy. It's very important that you can have natural sources to recycling, because the demand is high. 95% of this battery is made in China, Korea, and Japan. So safety is issue. So we can see that sometimes you can see fires or like iPhones or others. So safety is the key. So we are resolving the safety by using iron phosphate or other material very safe. Cycle life is key also. So we are looking for, especially for energy storage. On your laptops, iPads, many of your cycle life is around 500 cycles. We are looking here for 15,000 cycles, so means over 20 years. Utility company don't like to change, or the maintenance must be free. So we're going to use long cycle life. What means cycle? When you use your battery, when you discharge for all the day and you're charging by the night, this is, we call it one cycle. So, and also the fast charge. We need to charge. For example, let's see when you have the wind or solar only for 1 hour or 2 hours, we need to have fast charge batteries in order that we can get 100% mainly of the power. So I switch to what we call it fast charge. This is showing when you have like two technology, LFP or NMC. This is when you see the home. Both of the technology works very well. And then when you have less sun, when you have fast charge cells or batteries, that you are able to use all appliances in the home. For example, when you see that battery cannot fast charge, you cannot use air conditioning or cooking. So fast charge are key. Because this is just explain what Hydro-Québec is developing, 3 times fast charge, what you can see in NMC or in Tesla battery or other batteries. So our technology is around the world is using on Australia off-grid, in India also for substations. Before we have a joint venture with Sony, so we developed this technology for 4 years with Sony in Japan. So when you go to the energy storage, you can see this is, the question was given for 400 US electric utility executive. And you can see number ones that all the utilities need energy storage. 53% of the response are they putting their strategy orientation on energy storage, and the second one on energy efficiency. So application of service, but we have a lot of technologies here, so each technology had advantage. There are not any win between technologies. So technology depends also on geography, also on application and cost. So I'm not going in detail, but if you're interested in my presentation, I can send it to you by emails. Other thing also, the costs are very important. If we are using lithium-ion batteries, we need to have the cost less than $100 by megawatt hours. So if the cost is high, it will be very difficult. So other application for energy storage is deferred post-investment. This, of course, in order to invest like 50 to 100 million in substation, you can just invest for 20 millions for energy storage, and then you can put battery or other technology in your substations. This is very interesting report of India National Lab showing all energy storage for power grid. You have many applications, peak shaving, and also auxiliary service, distribution infrastructure service, and so on. Energy storage, they have a lot. It can be battery, it can be hydrogen, and so on. So, as I said, load leveling, ramping, peak shaving, and also this technology, frequency regulation are also important in USA. So the battery also can help for this kind of applications. So this is what I said about frequency regulations. So especially we need to have fast response. When the battery has fast response, it's marked about 1,000 to 3,000 $1 by kilowatt hours. It's a very attractive market for battery and other for frequency regulations. So frequency regulation market, as you know, we need to be sure that the battery, as I said, SOC means state of charge is 0% to 100%. So we need to be sure that our battery can be charged fast because the demand is between minutes, 1 minute to 15 minutes. Other thing also, Hydro-Québec or it's off-grid. We have many 15 or 20 off-grid here in Quebec, and we spend about over 200 millions for gasoline. So the battery with the solar or wind are also one of application for off-grid. Other thing also, you can have a hybrid system. So you can be connected, and let's see, in the big shaving, you can use the battery and smart grid to upload and download the energy from the battery and for other sources. Substation peak shaving, as you know, especially here in Quebec, when the winter is very cold and is like minus 30, minus 40, sometimes we call by radio and TV to the people we need to have less consumption, especially at 7 o'clock morning or 7 o'clock p.m. But however, if you use energy storage, we can use peak shaving with this megawatt hour battery and so on. So you can see that peak shaving, this is compared to substation 1, 2, 3 that we study in Hydro-Québec. So they are a way to use huge megawatt hours for peak shaving in some place. And we have already put 2.4 megawatt hours in the border of USA and Canada here in Hemmingford substation. So I finished that the large capacity technology for energy storage, we need them only in your iPad, iPhone, which is watt-hour energy storage. Electric vehicles, we're going to see acceleration penetration of electric vehicles in next 5 years, especially also what you call it automotive cars. And I believe for solars and wind energy storage, there are many solutions, not only battery solution, but there are many solutions. And thank you very much.
I know nothing about energy storage technology, so this is very intimidating. Going second here. I do know something about something though, and what I will be talking about is basically the long-term role for energy storage. Effectively, what are we going to ask of energy storage when we get to the place we think we want to go? And the place we think we want to go, specifically regarding sort of greenhouse gases and renewables. So Evolved Energy Research is a consulting firm that I started 3 years ago. We build models to model the energy system out to basically 2050. But basically the point is we are modeling the systems that we want, not the systems that we have, but we're modeling the pathway to get from A to B. So we're going to focus a lot in this presentation on what that system will look like in the long term and the implications for what we are going to need from energy storage technology sort of along the way. So I'm going to rely pretty heavily on a US analysis that we did last year. Here are some benchmarks for a low carbon energy system transition. This is what we call the 3 pillars. The 3 pillars are kind of the most robust result of energy system decarbonization analysis kind of in the world. So if you do a decarbonization analysis in China, India, Britain, France, the US, anywhere, it's going to have these components of decarbonization. So the 3 pillars here are end-use fuel switching to electric sources. So our decarbonized energy is primarily solar and wind, to be honest. And so we need basically to have our end-use energy demand be electric so we can access that energy. So we need fuel switching, we need electrification, we need a lot of that in transportation. But we also do that in buildings where those are current fuel uses. The second, the one I'm really going to focus on here today, is the implications of decarbonizing electricity. So everybody has seen renewable costs over the last couple of years. We don't generally talk about some of the competing technologies as much. So I think we can pretty categorically state that it will be a pretty high renewable future if we do decarbonize electricity. And I'm going to talk about some of the implications of that. But we're talking sort of a 90%, even 100% decrease in emissions from generation of electricity. And finally, energy efficiency. So some of that comes along with electrification, but we also need energy efficiency just because we're going to be building a whole lot of wind and solar and transmission and all sorts of infrastructure, and it would be nice if we could build less of that, and energy efficiency is one way that we can go about doing that. So again, I'm going to focus mostly on pillar number 2. Pillar number 2 is decarbonization of electricity. So this is a map of a country that refers to natural gas as freedom gas, but it also is a country that has 100% clean or renewable goals in quite a few jurisdictions. 100% clean electricity is a fundamentally, obviously, different system than we have today. And so you can see in California, a lot of jurisdictions in the Northeast, some of those are 100% renewable, some of them are just 100% clean. But these are very politically popular policies, even in the absence of a broader climate portfolio. So they take advantage of rapid cost declines in renewables. They're straightforward, and they can show demonstrable progress. They're at least politically straightforward. They are technically challenging, and I'm going to show sort of why here. How do renewables present unique challenges for balancing? So electricity system balancing is we need to match our sources of generation with our demand for electricity at all time points. So every moment that we generate electricity, we have to consume it. So renewables are difficult because we don't actually control their output, obviously. We can turn them off, but we can't economically control when we turn them on. So there's a high amount of variability. There's a high amount of uncertainty, so we can predict it, but we can't predict it as well as potentially we need to if they are forming the backbone of our electricity systems. New locations, so we could, more or less put generation in places that we wanted to before. Now we're really constrained by the best renewable sites. And then finally, inverters versus synchronous motors. They're just technical characteristics of generators, of renewable generators that the grid is not used to handling. As I said, electricity balancing is matching supply and demand through time. It's also power quality, but I'm really going to focus on the first one here. So how do we go about doing that? Energy storage is an obvious answer, right? You charge when there's excess, and then you discharge when there isn't enough. That's sort of the simplest way of describing it. It's sort of the simplest concept. The difficulty is that balancing challenge fundamentally changes as we get more and more and more renewables. So what we need at 30% renewables, 40% renewables, 50% renewables is very fundamentally different than what we need at 80%, 90%, and 100%. So this chart shows the spatial scale of balancing challenges. So whether that's on sort of an interconnection-wide basis, transmission basis, or a distribution basis, and then the time scale on the bottom of the balancing challenge. So that's in seconds. And as you can kind of see, as we move further along in terms of our renewable deployment, we're going to start hitting very different problems. Whereas right now we'll hit issues of regulation and area control error, and then we'll get to sort of ramping and minimum generation issues. I don't know if people are familiar in California with the duck curve. The duck curve is a balancing challenge for California because it has too much solar in the middle of the day, and so they are planning in sort of the next 10 to 15 years to deal with that with a combination of solutions, but that is still a relatively near or medium-term challenge. As we get to sort of 60%, 70%, 80%, we get situations where we have basically days where we have too many renewables, and even weeks where basically renewables are over our demand for them for persistently for a couple of weeks. That's a very difficult challenge for the types of things that we're talking about today in terms of some of the battery technologies, and I'll talk about kind of the scale that each might need to be deployed in those types of systems. So this is a kind of a confusing chart here, but the top one is basically our net load in a reference case scenario. So this is kind of what the electricity system is used to dealing with. So, there's some seasonality to it, right? This is the Eastern interconnection. There's some seasonality to it. It's peaking in the summer, kind of going up and down relatively predictably over the day. And this is net load. So this is load minus our variable renewable generation. The top scenario just doesn't have very many variable renewables. The bottom scenario has quite a few variable renewables, obviously. And what you see there is sort of rapid fluctuations between way too many renewables and way too few renewables. You can imagine sort of balancing between those sort of spikes with some of the energy storage technologies that have been deployed today. The difficulty is, if you notice, there's some real periodicity to it. So basically, you have a situation where you have too many renewables, basically all sort of late winter and spring. What that means is, if you want to balance that system without curtailing, you would have to basically store energy in March, keep it for a long time till it warms up, and then discharge in August. And that's kind of obfuscating that there are also some, 100-hour charge and discharge cycles too, but that's kind of the fundamental issue, is that you start running into these challenges that are appropriately defined as seasonal in nature. What that means for what we need in terms of capacity on the system that isn't renewable. Basically, if you look at the left, that's the reference case. You can see that we have a lot of capacity that requires sort of discharge durations, and by discharge durations, I mean they can stay on for 10, 20, 30, 40 hours because they have sort of energy to support that type of behavior. The obvious resource that has that type of thing is a thermal generator. It can draw on basically an infinite supply of fossil and burn that for a long discharge duration. Batteries are more difficult. Obviously, you have to have charged so that you can discharge for that duration. So on the right, you can see our high renewables capacity curve. There is quite a lot of room for storage devices that really only need to be able to discharge for 8 hours economically, or basically they need to have sort of 8 hours of discharge duration on the system. The difficulty is that we still have about 350 gigawatts that needs a duration in excess of 10 hours, and about 300 gigawatts that needs 50 to 100, and then we still have 100 gigawatts that needs over 100. We're not, a lot of the battery technologies that people think are just going to be the panacea to 100% renewable scenarios are really going to struggle economically to meet the needs of the system over that discharge duration. So we need more technologies. The technologies that we're deploying today in terms of energy storage are very useful. They have a huge role to play in some of those what I'm calling needle peaks here, so kind of 6 to 8 hours. But we need kind of fundamentally different technologies that start having durations of, in excess of 100 hours. And it may be that it's an alternative to battery storage. It could be electric fuels. It could be, Martin would like me to say K's here, I'm sure. But K's is certainly something like that. And even existing thermal generators can provide that type of thing. So we just basically need to keep our eyes open to the long term in terms of what we're going to be asking of energy storage. So thank you.
All right. And our third panelist, Martin.
I'm now used with the Mac, so I haven't played with a PC for a while. Bonjour, bienvenue. First, thanks to the IAE organization, Pierre-Olivier Pinault. It's a pleasure to be here today. How many of you are outside of Montreal, are from outside of Montreal? Well, that's quite interesting. So welcome. I hope you enjoyed the last couple of days here. So my name is Martin Larocque, CEO of Sigma Energy Storage. We've been around since about 2013. So I'll try and entertain you for the next little while with my French accent, and I hope it's going to be pleasant. Let me start with a little story, maybe outside of that presentation, but I have a daughter, and last week she had a homework to do about what she wanted to do when she would be older, and she's in grade 4. So she asked me, Dad, what did you want to do when you were my age? And I explained to her that I wanted to start a candy company. And I was passionate about explaining that, and then I finished my story, few minutes. And she looked at me and she said, so Dad, you really failed, huh? So I hope that down the line she's going to understand that her dad is trying to put up a solution that's going to make this planet better, and that's what we hope we do at Sigma Energy Storage. So our vision is that compressed air is a commercially available technology that is a utility scale solution, suitable for very massive amounts of energy storage, and that allows grid operators to balance their supply of intermittent renewable energy. There's a limitation, seems to be about 20 to 30% in the market, over which, when you start introducing more intermittent renewable, you create all sorts of issues for the grid operators. So we hope energy storage could resolve a part of that issue or these issues. I always like to start with the team. So we are a dedicated team of 11 employees nowadays. Based in Montreal, we have an office nowadays in the US, Massachusetts, an office in Toronto, and our core team is located here in Montreal. PhDs from McGill, from University of Sherbrooke, from Polytechnique Montréal. So we have a few employees that are quite a good background in terms of engineering and design and mechanical engineering mostly. If we look at what we're trying to resolve, and I touched on it a little bit, we see a challenge with solar. We see solar is very predictable. Ben talked about the duck curve. It's predictable that it's going to generate electricity during the middle of the day. Grid demand mostly is in the morning. The peak demand is in the morning and at the end of the day. So that's not properly aligned. Same with wind. Wind is even worse. Wind produces energy at any time of day, so you can predict. You can put a wind tower and predict how much wind or how much energy is going to be produced on a yearly basis, but difficult to predict when during the year it's going to be produced. So that adds to the challenge of implementing the renewables. Same with tidal. We were talking about it earlier today, but we're working some projects where tidal energy is quite interesting. In the Bay of Fundy, we have a couple of places here in Canada that are quite interesting for tidal. It produces about 4 cycles of energy on a 24-hour basis. Of which 3 or even sometimes 4 of these production cycles are misaligned with the demand. So that creates then again a challenge, which is to fit the energy production with the low demand, the low profile, I should say. So the misalignment is the key market driver for a technology like ours, and that's what we're trying to resolve. It is energy storage in general term is called the holy grail of the energy market. Going forward, people are talking about how many billions of dollars people are going to spend on energy storage. When we look at it, and there are so many different applications, and on one side, and there are so many different solutions on the other side. And at the end of the day, it's trying to make both of these things fit together. It's about finding the right solution for the right application. When you do that, the economics are going to make sense, and all the characteristics of the solution you're looking for are going to start making sense. And that's how you're going to reach these very large numbers. At Sigma, we have developed 2 different solutions for 3 different applications. I'll briefly walk you through the 2 different solutions, and then we can talk about the applications maybe later on during the panel. The system that we've started developing back in 2013 and even a little earlier is called the Hybrid Thermal Compressed Air Energy Storage, our energy storage system. This system is a mechanical device. It could operate for long, extended periods of times. We're talking about operation periods that are measured in decades. We're working usually 30, 40-year PPA contracts, and that's a key differentiator. We can work such a process at small scale or at very large scale. Just to give you a brief explanation of what it does, actually, it's a straightforward concept. Whenever energy is available from the grid, we start a group of compressors, small or very large. at which time we compress air that can be stored. Small size system, we store the compressed air in storage vessels, above ground cylinders that can be deployed anywhere. At large scale, we use the same process, but we store the compressed air in some reefs, either salt caverns or porous rock formations that have size that are measured in billion cubic feet, massive size. The complexity of compressed air, when we look at it from an engineering perspective, the thermodynamic analysis gives us a number of about 40% efficiency when you compress air and you use it to produce electricity back again. What we really focused on from the get-go was to try and resolve the main issue, which is to find a useful way to capture and store the heat that is produced at the time of compressing the air. So we have found such a process, actually few processes that allows us to efficiently capture all of the heat, most of the heat that's produced at the time of compression, and we store it for later use. This later use comes when it's time to produce electricity to be re-injected in the grid back again, at which time we're going to depressurize the air, whether it's from the storage vessel or the cavity, the underground cavity, at which time the temperature of the air is going to come down. So we use the heat, we re-inject it, create the expansion of the air, that then drives a turbine connected with a generator that produces electricity back again. I said exactly that to my mom, and she was looking at me saying, oh, that's impressive. Small scale with the market, the slide is kind of upside down. I think that's all good. On the microgrid side, so these are the kind of locations in which we're going to look to deploy our small scale system. Microgrids, usually compressed air at that size that uses vessel. Scale is usually few megawatt hour in terms of power capacity and energy storage. It can be installed anywhere. We use pressure rated vessels. It's reliable. It can resist to climates. And the goal, the intent there is to reduce the carbon footprint of these remote locations. We have such locations here in Canada. Many of these, actually there's about 270 diesel-dependent remote communities. These are all located up north in Canada. Climate is very harsh. I was explaining to Ben that I showed up in some of the communities. I did a little tour this last winter, and actually was in January. It was minus 54 degrees Celsius when I show up in some of these locations. Quite interesting. I thought I had a thick skin until then. But these are consuming a few millions liters of diesel on a yearly basis. It's a question of survival for them. They produce a lot of the electricity or the energy. They consume a lot of diesel to produce heat. Same with some of the mining sites all over the world. Actually, we figured about 25,000 environments that are diesel powered worldwide, in which we could implement a small scale system like the one that we have developed. That represents a large market. We hope to be able to save between 40 and 60% of the diesel. When I was talking about our process, we optimized the process specifically for a diesel environment in which we can capture and store the heat that we create with our own compressed air, but we can also capture and store heat that we capture at the exhaust of the diesel genset. So that makes theoretically a system that can be even above 100% efficiency. Why? Because we're cheating. We're taking something that was going to be released in the atmosphere, not being used anyway, and we we find a useful way to use that heat. For every liter of diesel, we're removing about 2.7 kilograms of GHG, which is quite interesting. Large scale is probably where the energy storage brings the most value. In typical environments, if you have a solution that is not large enough, you don't have an impact. We look at and nothing against the battery, Karim, But when you look at the largest battery that have been implemented right now, it's in Australia. Australia had deployed using Tesla/Samsung about a 129 megawatt hour battery. A few other projects are coming. The few projects that we're working on using our technology and our process are in the scale of 8 to 10 gigawatt hour. We're talking 70 to 80% the size of the largest battery deployed in the world. As mentioned, these are applicable in environments that have deployed a lot of renewables. Intermittent renewables, I'll give you an example. Ontario. Any of you from Ontario? No? So I can have fun. Ontario is decided about a decade, 12, 15 years ago to remove all of the coal and to replace it with intermittent renewable, a lot of which is wind. Very interesting concept. But that created for Hydro One in the IESO, so the grid operator, instability that they hadn't managed before. Coal was not good for the environment, but very predictable. Dispatchable power, wind is not. So for every watt of wind that they've installed, they decided to go with a peaking power plants, because when there's no wind, you still need to fill the demand. So that creates actually two different issues. When it starts to be very windy at night, which is the case in for many months during the year, they end up with too much energy. So what do they do? Actually, two different things. They sell negative pricing electricity to us here in Quebec and to the US. So you think about the concept, they've invested tens of billions, and then they have to pay to get rid of the electrons when they're being produced. It doesn't make too much sense. On the other side of the spectrum, daytime, when there is not enough electricity and there's no wind, they need to start the peakers. So they pay high cost electricity, actually, on the nominal cost of electricity generation in Ontario. That's the highest, the peakers. And they produce a lot of GHG. So a large-scale energy storage device like ours can resolve these two issues. At night, when you produce too much, you store, but you need massive amounts. And then during daytime, instead of starting the peakers, then you can use the electricity that you've stored, low cost, completely green. That just makes a whole lot of sense. So we are working some of these projects, few locations. The complexity for this type of solution is to find the right geology and to have the geology located at the right place. I'm not a geologist, but we have found many of these actually, and actually in Ontario they have a lot of porous rock cavities that we really like. They're already pressure rated. They use, actually they've been using them for decades now. So that's interesting. They were storing natural gas during the summer, and they were using that natural gas to heat up the homes. But nowadays, these geology are no longer being used, so they're depleted, just not being used. So we're looking at repurposing them and use them for something useful. I was talking about Ontario. We see that all over the world, in Alberta, in Indonesia, and Chile, in China, in Australia, everywhere that they've deployed a lot of intermittent renewable. There is a case to be made for a lot of storage. Last solution, actually, and I'll just skim very quickly through that. I think I haven't checked the time, but we found a solution. Actually, we extracted the subsystem that is our thermal energy storage subsystem out of our process, and we applied that into an industrial environment. A lot of industries, a lot of industrial processes are producing a lot of heat. So we found a way to capture and store the heat that was going to be wasted by these industrial processes. At the right time, we can transform that heat into producing electricity. That makes it quite interesting for many of these industrial sites. We typically look at a discharge cycle of about 4 hours daily. We have seen, then you can do energy arbitrage. We see a lot of jurisdiction where the pricing of electricity for specific hours or predictable hours during the day are going to be quite expensive. So in these cases, we could store heat. It was going to be a waste, and just produce electricity back again. We have tweaked that a bit. We have few patents on that, but we found out that on many occasions, the wasted heat is a big mass of thermal energy, but it doesn't reach quite the right temperature for us to be useful. So we combine that with either CSP or PV, and then we can augment the temperature of that mass and then make it very useful. If this thermal energy is not being used on a daily basis to produce electricity, we can use that heat and do something useful with. Many of these processes they have boilers, so we could preheat some of the water that goes in the boiler. That eliminates a lot of usage for natural gas and other kind of things. So that's quite interesting. The business cases are usually quite good, looking at payback times, usually less than 5 years, which is really what industrials are looking for in all these cases. We see pricing arbitrage or pricing difference that are quite high in Ontario, New York, Massachusetts, California, Hawaii, all over the world. Competitive advantage, quickly to finish with, it's a mechanical device. It's another way of thinking and seeing the world. Battery is more chemical or electrochemical. We look at it from a mechanical perspective, say how can we build a solution that's going to make sense, that's going to be scalable, and then that's going to be non-emitting at the end of the day. We have built an ecosystem that's quite interesting all over Canada. Actually, we're doing the same nowadays in the US. We've been a few times in Europe. We've been approached by the State Grid of China. They said, oh, we have a small project in a remote location. We started asking questions to find out that it was a 200 megawatt little project. So what we're doing here, we hope to be able to replicate it everywhere in the world. We've gained a few prizes here and there. Here we go. Thank you.
All right, so thank you to all of our panelists. We'll now open it up for questions from the audience, and if anyone has any, there are a few microphones set up throughout the auditorium.
Hey, I'm Greg Upton from Louisiana State University Center for Energy Studies. So the question that I have, and I think each one of you might have a different perspective, but if we think about a future where you have a lot of intermittent renewables and a lot of storage, there are different places where the storage could be. It could be really large utility scale. It could be all the way down to small batteries in the home. It could be batteries or just different types of storage at the distribution grid. Which do each one of you think, and do you have an idea of what that might look like?
Yeah, it's an interesting question. So it can be like place by place. Let's see if you can see in Germany, for example. So in Germany, they focus on solars and also on battery in the homes. So this is case by case and geography by geography. Let's see in Africa, so we can see this is very close to the cell phone coming to the market. Before in Africa, there was phone lines was very difficult that they get phone in the home. And when the cell phone coming, so all Africa, they can using cell phone and so on, in order to build the productions, transmission line and distributions. So you can build with a small village. You can see, it depends when in Tanzania or others, when you have the solars and you have battery or other technology, and then become like a distribution community with a few megawatt hours and so on, or some village with schools that you need like a few kilowatt hours of battery and so on. So this is case by case. But I believe the market is when usually, especially on the battery, same technology in your cell phone, you can use it on kilowatt hours on home use and megawatt hours on when you have like megawatt hours for solars and wind and so on. So it depends on geography and also the space. Let's see in the Singapore, for example, space is issue, which you cannot use solars or something. So you can use like, I don't know, some wind, offshore wind, and then you can build some batteries under some parking lot or something like that. So this is its key, but there are multiple functions or solution for each country and each place.
Karim, he's the one holding the patents, so I won't contradict him.
Okay.
I guess the answer to that is that there's no straight answer. There are many different applications and there are many different solutions. As technology providers, sometimes we tend to look at it from a technology perspective and see where it could fit, but I think it should be done the other way around. So utilities, grid operators should try and understand what problem they're trying to resolve, and then you look at it from the other side and try to understand what technology fits the need. And when you have that combination of understanding what you can do with the energy storage, because the market is so vast, at the end of the day, you need to look at it from a needs perspective, and then you build the case backwards to understand what technology is the best suited to answer that need. On many occasions, and I feel that because we're bringing to the market something that's different. The first thing that comes to mind is to do energy storage using batteries. And in many occasions, that's going to be the right solution, the right fit. A cell phone, a car, a small duration device, but sometimes it might be something else. So that's what I'm trying to bring as a perspective every time, is to try and understand what the need really is, and then you scale it back to what technology can answer that need.
If I can get the mic. It's already on. Oh, it's already on. That explains it. So short duration applications, so kind of 0 to 8 hours. I think it can kind of be anywhere, to be honest. I think there's a lot of rationale for a lot of that to be distributed to avoid distribution assets and needs for sort of investment, especially if we electrify. Longer than 8-10 hours, I mean, that's a grid scale, like transmission level solution, in my opinion. I mean, if we're going to 100% renewables, we're not going to have to curtail 30%, 40% of renewable energy. So we need something probably different in those types of cases, but it has a lot of batteries at the distributed level that are shorter duration. As you saw, there was the kind of needle peak issue still exists. It's just there are kind of additional issues that will have to be managed with something else.
If I can just add, to sort of build off of that question, Ben, so you were talking about modeling electricity systems looking out to 2050 and describing the sort of seasonal energy storage need. And so do you have any view from your modeling exercises as to what could potentially serve that need? Because you kind of alluded to batteries may not be the most practical solution for seasonal energy storage, but do you have any views on what might be?
So there are, I think batteries make a lot of sense up through, this is based on today's costs. I mean, I've been wrong on battery costs every time I've ever said anything. So, but there are some sort of fundamentals of battery storage technology, and the fact that you have to actually sort of build the duration that are going to be challenging once you get past durations of greater than 24 hours. I think electric fuels are one potential option. So hydrogen electrolysis, basically, and then either stored directly as hydrogen or made into synthetic methane or even synthetic liquid fuels. Honestly, thermal generators of different types. People don't like to hear it. People want 100% renewables, and they want 100% renewables with batteries. But thermal generators are, things that can discharge for greater than 100 hours at a relatively cheap cost. Those can be fueled with different things, right? Those can be fueled with synthetic methane. Those can be even fueled with hydrogen. They can be fueled with biofuels, but they don't have the problem of needing to kind of build the duration and store it. So I think, as Martin said, the solution there are a bunch of different applications, and thinking of applications in terms of duration is really important to understand, like whether things are going to be competitive really at some of these sort of 100-hour type of applications.
If I can build on that, it's an energy economics conference, and that comes back to always a financial question. At the end of the day, you need to be able to build a business case, demonstrate the efficiency, not of the technology or the infrastructure you're about to implement, but the efficiency of the dollar you're about to invest. And if you can do that efficiently, you have a winner. And that's how we kind of look at it.
think we have another question from the audience.
Right. Thank you. Very good presentation, discussion. We talked about many fabulous technologies and the benefits for the energy storage system can bring us. But what if we operate energy storage system in another way? It can reduce peak demand, but it can also increase and push the price higher to make other generators earn more profit. It can help us to integrate more renewable solar and wind, but it can also help us to integrate much less and make other resources take advantage in the market. And there are also many other things. I mean, each benefit you discuss, we can find another way to operate and to make such loss, but to make other players earn much more. So do we need to worry about that? And if we really worry about that, what we can do to prevent such scenario happens? Thank you.
I mean, I classify energy storage as an enabling technology of renewables. Basically, the scale of that in terms of the positive that will sort of have in terms of reducing emissions outweighs any sort of, I think, short-term marginal negative impacts. People talked about in California, if we installed storage, there would be arbitrage with sort of out-of-state coal and things like that. And I just think they're very short-term concerns, and they're not worth discussing when some of these long-term concerns are basically kind of rising to the fore and actually approaching a lot faster than we expected due to renewables costs. So.
Then again, I like to see things the other way around sometimes. In many jurisdictions where we have, we're discussing nowadays, people are thinking first about installing renewables, different types. And then they're thinking about storage down the line after they have felt some issues about how can I integrate more than 20, 30%. I think we could probably most likely look at it the other way around because storage is the solution that offers you the dispatchable power. So there's no limits in terms of how much storage can you install. You can install as much as you want, as much as there's a need. And then you can look at the renewables being the mean and the way to fill the storage. And then you can define the size of the renewable based on storage and not the other way around, because you'll never be able to install more renewables than 20, 30%. After which, if it's that intermittent, then you have an issue. We've seen that in Chile, where pricing of electricity in the middle of the day is close to zero. Too much solar. So that's kind of, then again, like Ontario, too much wind at night, cost of electricity is zero, negative. So these are the kind of impacts, negative impacts on the financial side that are quite interesting to see. So looking at it from the other way is to install the storage first, and then you define how you fill the storage, how much solar you need, how much wind you need to make sure that the dispatchable power is ready to go whenever you need the power to be injected in the grid.
All right, I believe you were waiting next, so.
Hi, this is Mohamed Ansarin from the Erasmus University at the Netherlands. First of all, thank you very much for your presentations. They were very insightful. I personally don't have any doubt that there's going to be a lot of need for storage in the coming years, especially with renewables growing so fast. And they also don't really have much of a doubt that manufacturers in the US and in East Asia will be able to keep up with that demand. But one thing I don't really understand, or I kind of have concerns about, is whether we would have enough raw materials, the basics, flowing in for batteries to exist. I just stole this gentleman's question, and I guess I'm pretty good at that. And I saw another guy sit there, so maybe I'm just really good at this. But
all right, so you asked the question for several people.
And yeah, so I'm shooting 3 birds with 1 stone. Basically, I'm kind of concerned about what would happen if we run out of lithium supplies in Chile, or if rare earth metals start drying up, or they just become harder and harder to excavate. What are your thoughts on this issue?
So if I just give you some history first, so we can see that the patent of lithium-ion and solid-state battery belonged to North American Hydro-Québec company, and we can see, as I explained, 96% of all production is in Asia, Japan, Korea. So 1991, Japan, and then switching Korea and Samsung, LG, and now is switching China, which we call it ABC, ATL, BYD, and CATL, where they have today over 70% worldwide productions. So in order that we have, as I explained during my presentation, this what we call it circular economy and green economy, we need to have ecosystems here in North America, very important. You cannot bring the factory here for battery and then you can get your supply chain in Asia. And especially we have here many natural sources. I know very well Quebec, I don't know other parts. So in lithium ion, you need copper, aluminum, nickel, cobalt, and graphite. And all natural sources are here. In order just to sell natural sources, as in Africa's Congo, Brazzaville, with the kids are working with low cost, we need to have first and second transformation of our natural sources here. And we need also the government at least has 50%. Because if you just sell natural sources, you lose. And behind that, when you have the ecosystem, we have the technology here, and also we can be competitive in the cost because we have good school, good engineer, good technician, and we can make automatizations. When you have automatization of the factories and so on, and you can build, and the market is huge, so there's space for Asian and so on. So I believe another issue is also we need the money because if you like to have like a 35 gigawatt hours factory, we need $5 billion. So this is one for gigafactories. So natural resources are very important, factories are very important, and because limitation of lithium sources, today lithium is in Chile, Argentina, and Bolivia. We have a lot of lithium here in North America, especially in Quebec. So recycling becomes very important. So we're going to have mine of natural resources and urban mine coming from recycling, and then we can arrange that we can produce this kind of the materials here as battery grade for our own market in North America and also a worldwide market. You can see here because we have, free trade between Mexico, USA, and European and so on. This is also a huge market that we have with Europeans, South America also, and Asia Pacific and so on. So we have the market, but we need also, I believe, we need to think about consortium between private company, university institutions, and also government to think about the strategy is very important in order to create jobs and keep also, because the battery, let's see, in China become national security. So this is the key.
Yeah, I just worry about it much more in transportation than I do on the grid because they're, low density technologies that I think could substitute on the grid if it was sort of constrained on the lithium ion side. So, but transportation is a different animal, and that would be my primary concern, but not really for the grid.
So we need to think about a mechanical type device.
Storage first, and mechanical storage at that. So.
If you don't mind, I just wanted to just ask a quick follow-up. So you did mention material recycling, Karim, and how are there major sort of technical impediments to actually being able to recycle battery or other storage materials that still need to be?
Today, many of recycling technology is using pyrometallurgy, that means that they just heat and then only cobalt, they recycle cobalt. I don't think this is the solution. Because the electricity is very cheap here, we can use some electrochemical method like hydrometallurgy, and then selective we can recycle all of the battery. Today, our process, we have some consortium here in Quebec with some engineering firm and also other company. So our goal is to recycle 90% of our materials.
But it's quite energy intensive.
Yes, energy intensive, but when you cost here, you have green energy here and very low cost here in Quebec. So they are not big issue on energy here in Quebec.
Okay, so you still have another non-material question?
Exactly. So okay. I expected that the answer about sustainability will make compressed air actually a nice solution. So that I wanted to ask you about acceptance. Like, are there any issues about acceptance of these systems? Do they cause like some disruption in the system where they are located and so on? Thank you.
You're talking about acceptance of compressed air energy storage?
Yes.
I think there's a lot of education to be made. There's a big project that had been implemented in Antwerp, Germany, one other project in Alabama in the US. So there's a lot of talks nowadays about implementing more compressed air in California and Texas and different places around the world. The acceptance is fundamentally based on financials. We're back at it again, but that's the core and that's the fundamental. Then again, it's always about the efficiency of the system, but it's mostly about the efficiency of every dollar that's being invested into the project. As more people deploy more and larger scale renewable energy production sites, there is going to be a need for larger scale storage, and we hope to be able to compete. So for us, it's about making sure that people don't only evaluate the solution they know most about, which is in many cases batteries. Tesla is making a lot of hype, so is Panasonic and Samsung and all of the others. Actually, I was in Germany, in Dusseldorf, in a trade show. I've been there for a couple of years in a row. It's called the Energy Storage Europe event, a conference. It's one of the largest in Europe. 90% are battery manufacturers of the people presenting there. Few on the hydrogen side, and there was actually 2 companies on compressed air. So we're starting to be in these conferences. There's a lot of education to be made around what it does, where does it fit, and how does it fit financially. So I think there's going to be a lot more acceptance. It's about also creating the proper credibility, installing few sites. Since we're using some geology that are well known, that have been used for decades, there shouldn't be any issues on the environmental side or on that front. It's pretty straightforward. We use cavities that have seen pressure in the past, so there's no risk there, especially if we use a cavity that's been used before. And on the equipment side, then we see a lot of manufacturers offering different types of solutions for compressors, for turbo expanders, and so that's pretty straightforward.
Did you have a question there, sir?
Yes, one question and one comment. So, Joël Brideau, I'm from Grenoble Institute of Technology, where Dr. Zaghib got his degrees. My comment is about Ontario. Do not forget that in Ontario, when they get rid of coal, half of the path was done through nuclear energy increase also. And then my comment is about the very nice graph where you show the different time sequences and what the level of power are needed. So we have discussed a lot about storage, but here a lot of people are working on demand response, and to some extent, demand response answers to some of the needs, probably at the hour scale or daily scale. So how do you feel the competition with this? Because if there is some market design that is done to give money to them, then it will be less money for you. And then I have the same question more or less at the 1,000 hour scale. If there is some people that are producing those services, they may be able to produce all the services at lower scales. So once again, they are going to get the money, and you will not have the money to invest in your capacities. Thank you.
So in terms of demand response, absolutely. Sort of that really steep peak, which was like a couple of hours, I mean, it's perfect for demand response if we can get it. I would much rather not have to buy something to do something instead of just using something intelligently. It just sounds better, right? I think I'm certainly hopeful, and I also think like as more of our electric load becomes space heating, water heating, and EVs, the potential for demand response goes way up. Those are kind of the principal ones that would be used for demand response. So totally agree. Hope that gets developed so that we can avoid some of that new capacity need, because that, infrastructure is a huge problem in these systems, having to build all of that stuff. In terms of longer duration, solving shorter duration problems, absolutely, which is one of the reasons why, some of the short duration services that people are kind of banking on technologically are really going to get swamped as soon as the longer term needs get, you have to deploy capacity for balancing. So, for example, like the regulation market in California, they have 1,350 megawatts of storage that was mandated. The regulation market is 300 megawatts up and down. So already, like, you're twice the size of the hourly regulation market. So, I think it's a very important point that long duration would basically compete for some of these, relatively shallow short duration services. The only thing I would say is you're never going to build a 100-hour duration storage facility if you only need 8, So there will still be some shorter duration capacity that will be deployed just because it's more economic for capacity needs to deploy something instead of sort of over deploying on an energy basis.
We talked about some economics, and maybe I bring up that's a good setup for some of the discussion we had earlier on, but people understand the value of seasonal storage. But what the value at the end of the day is $1 per kilowatt hour. When you have a solution that has that has few cycles, and let's say it's a few cycles every season, then the financials cannot make sense. It's very difficult to make a financial justification out of that. So the large-scale solution allows you to build an operational pattern that embeds some seasonality, but that delivers power on a daily basis. That's how we look at it from an operational perspective for compressed air, since we have that large scale that allows us to do that. You talked about Ontario. Ontario, they removed a lot of coal. They are about to start refurbishing some of the nukes that they have in place. And they have installed over the past decade about 6 gigawatt of wind. And that is, actually it's the combination of the load or the production that is predictable from the nuclear. Very difficult to make it vary, so by a little margin. So they have a base load that's nuclear, on which it varies quite a bit with all of the wind that they've installed. That's the fundamental problem they have.
So Laurie Schell with Empowered Energy. There have been passing references in the discussion and the questions and answers on hydrogen. So I'd like to ask the speakers to more explicitly address the potential they see, particularly as renewable penetration increases and the ability for the long-term seasonal storage.
Yeah, if you, I start just to explain energy density first. The maximum of the battery they're going to conduct us next 10 years, not higher than 500 watt-hour by kilograms. Today, the gasoline and the petroleum, the energy density is around 11,000 watt-hour by kilograms. And then when you switch to the hydrogen is 30,000 watt-hour by kilograms. So only 20% is a huge energy and so on. For example, let's see, I can give you our case here in Quebec. We have a huge excess of power. And then you can just make electrolysis, and then you can use hydrogen for many applications, like ammonium application chemistry. You have carbonator, so you can use CO2 captures, and then with hydrogen you can going to have any green gases, and also the mobility and also transportation, because the battery they have limitation only for small cars, but when you have like trucks and I don't know, train and so on, you need hydrogen because energy density is very high. The disadvantage of hydrogen has high energy density but low power, so we need to combine the battery and the hydrogen together. So hydrogen, when you see, because the people, they don't know about hydrogen is very safe. Even when you have the flame, you can touch. But compressed hydrogen is very difficult. Today, we have, I think Japanese going to introduce in 2020 Olympic Games, which hydrogen become focus for them. They're going to produce the power by hydrogen, buses, and transportation by hydrogen. What they're doing in Japan right now, they're using coal in Australia, and they, it's not green, and they're producing hydrogen, and they to make transportation of hydrogen. So transportation become not issue because today we can make transportation with liquefaction gases. So we can have liquefaction of hydrogen bombs minus 231 degrees C. So we can transport that. But we need to have green sources in order to produce hydrogen. But I believe in the next 20 years, 30 years, hydrogen will be change our life because of very high energy density. And of course, hydrogen is, in the periodic table, is the light element. And from the water, we can make hydrolysis. And we believe that what we call it fuel cells, they're going to play an interesting role for transportation or energy storage and so on. Very important, let's see, in the islands like Hawaii and, I don't know, other island in the Pacific and so on, because global warming change, and we're going to get some catastrophe and so on. The battery or other technology maximum that we can get energy storage is 1 day, 2 days. But hydrogen, they can get us energy storage for 2 weeks to 1 month. So this is, I think, a future for hydrogen will be, we saw it next, as I said, between 5 years to 30 years.
Any other comments? It's a good question. You touched on a little fiber. He holds a few patents on the hydrogen stuff.
Yeah, so when we do some of our deep decarbonization analyses, specifically when we start going towards net zero economies, synthetic electric fuels at some volume, not huge volumes, but at some reasonable volume are really cost effective. So hydrogen operating as a feedstock, either used directly or power to gas, power to liquids, supplanting the use of fossil fuels in chemical production, things like that. I totally agree that hydrogen is kind of core to those, to some of those economies.
Hello, Marcin Pikliński, Uniwersytet Ekonomiczny from Poznań, Poland. I want to ask about efficiency of air compressed storage and how much costs this per unit.
So the thermodynamic efficiency of a compressed air process is about 40% on the pneumatic portion. We combine with the thermal aspect, we reach around 70%. Different configurations are available. So when we look at efficiencies of a system, it can go full. Actually, if I scale back in time, I mentioned some of the projects, one in Germany, one in the US. What they do is that they use natural gas at the end of the process to heat up the air, create the expansion. That adds to the efficiency of the entire process. So we have built certain configurations where we could reach up to about 80% efficiency, but that would use natural gas. So if you want to go full green, about 70%. If you want to do a combination, some sort of an hybrid system, then we could go reach higher efficiencies. Typical cost at scale that we're looking at is about 5 cents a kilowatt hour. So that's typically the cost we're looking at. Working projects with PPAs, so 30 or even 40-year contracts. Obviously, the longer term the PPA, the lower the cost per month, per power, per unit. So depending on how you look at it, we're dealing with mechanical devices that have reliability records. Some compressors that are deployed in industrial processes or anywhere are being used since the 70s, 80s. So we know that these kind of equipments, they have a very, very long lifespan, and we capitalize on that. We try and make it efficient. We try and integrate as much as possible off-the-shelf equipments or components, and then we focus on making the process efficient. That's how we see the world.
Any other questions or comments from the audience?
I'm Pradyumna Bhagwat from the Florence School of Regulation, Italy. My question was about the interaction that you see between large-scale storage and electric mobility. because the V2X part of electric mobility can be a competitive resource, and how does it affect the business cases for grid-connected storage?
Okay, so this is also case by case. This is what you call it vehicle to grid. Let's see, because we can see that the next few years, fast charge will take place. Like today we have level 1, level 2, and level 3. Level 1 is 110, level 2, 220, and level 3 is DC with 50 kilowatt hours, but we're going to see 100, 200, and 300 kilowatt hours. And this one, we need a lot of power, and we need also to be sure that the grid are stable. And then energy storage, they can be, because these chargers are DC and the grid are AC. And we need to have a PCS, power conversion system. And behind that, you can use like a megawatt hours station to replace what you call it, the station of gasoline station. What means that by the night, you can charge these megawatt hour batteries, which is DC, and then you connect the DC chargers to these batteries, and so on become more easy, so you have not any PCS communication between DC charger and large energy storage. Other thing is very important also, as I said, I explained during my presentation, when you have like 1 million electric vehicles, and people want to make charging by night or by day in their home, so it's very difficult for the grid, especially in the same time. So we need to have a smart grid applications, and also the grid, they can have like, we allow you to have vehicle to grid and vehicle to home. So let's see, you are here for the meeting for 3 days, 4 days, and then you can have like your apps, and you send to utility company like us, I don't need my car for 4 days. What means that I'm going to buy the power from you, and I'm going to charge your car 100 kilowatt hours by night, and during the day, I'm going to use, I don't know, this is around 100 cars with 100 kilowatt hours, it's 1 megawatt hours. So this is vehicle to grid. Other, what we call it, vehicle to home. Let's see, as I explained, when you have like a blackout and so on, you have 100 kilowatt hours. You can use it to your home, and you can maybe share 50 kilowatt hours for your home and 50 kilowatt hours that you can go to other substation and so on. I believe energy storage and the vehicle to X and so on become very important, and also we was working on this area for over 20 years, and we are very active today.
Control systems integration is kind of the key there. So you need to have, to communicate with the grid, with the utility to have a certain amount of control. So I think that'd be nice to see. Hope to see that.
Any other questions from the audience? I have just one more. I'd just like to expand upon the discussion regarding hydrogen. So, and again, keeping in mind that, there are different needs and different technologies for different needs. But if we focus on, what you, Ben, described as this like 100-day shifting energy around problem, do you view hydrogen as potentially being a technology that fixes that problem in the 20 to 30-year range, or are there other technologies, or do we really not know?
So basically, I think my view on the use of hydrogen is probably different than other people's, and probably kind of different than maybe the subject of this talk. But basically, the role that we see for synthetic fuels is it more closely aligns your demand with your supply. So it doesn't necessarily, you're never necessarily returning that hydrogen to the grid in the form of electricity. You're just able to more economically deploy more renewables, because just you don't have a base level of curtailment that's that high. So hydrogen and synthetic fuels, and you don't even necessarily need to store it in terms of like hydrogen storage specifically. I talked about synthetic fuels. We have The US has 9 exajoules of natural gas storage. So you make a synthetic methane, you don't necessarily have to build more dedicated storage to store that in. So my take is that you use it a little more creatively, but it's not a device that you store it and then you produce electricity out of it 100 hours later. I still think you need, I personally still think you need a thermal generator at that duration, past 100 hours probably.
And so you view it as a thermal generator using fossil fuel extracted from the ground, or is it using
that thermal generator could use power to gas, could use biofuels, could use natural gas, could use, it's all subject to emissions constraints and whatnot. But that is not a lot of energy, right? That 100-hour duration resource runs 20, 30, 40 hours, runs 2, 3, 4 times. It's like a cap factor of 5%. It's not, it's not a ton of energy. So you can displace that with a variety of different fuels.
I don't know, any other views on this? Otherwise, I think we're right on time, so.
When I'm not, just I like to say that when you have a lot of excess of power, for example, when you are a utility company, and then you can produce this hydrogen because it's very cheap. Your electricity, you have the power that you are not, so it's very good business case. And then if you sell it and then you send this hydrogen in Germany by boat, and then in Germany they can use it as to generate the power. And this is also, let's see, another example in Japan, because after Fukushima, the problem was huge, and for them that they depend about some no stable country for their energy and so on. So in order to diversify, so they can use hydrogen also to produce electricity. Even efficiency is 50%, but when you have good business case that you are buying electricity for 1 cent, 2 cents, so hydrogen become very attractive. Now this is for production of the power, and they said transportation and other chemical application, I believe it will take place.
All right, so with that, I'd like to once again thank our 3 panelists and also thank all of you for joining us for this discussion.
Thank you very much.